So, again, we're going to be moving up the spinal cord today. First part's all about conscious sensation. Two major pathways there. You should already know these. What are our two major sensory pathways in the spinal cord? PCML, fantastic, and the anterolateral pathway, more specifically spinothalamic tract. That's going to hit the thalamus, and then eventually the cortex, and that's where the magic happens. We perceive something, either someone's touching us or something hurts. It depends on which pathway we're talking about. There's also some unconscious sensation that goes on, so anything that doesn't make it all the way to the cortex is still going to have some influence on nervous system function. Part of this might be in refining motor output via the cerebellum, and part of it might be gating painful signaling that's trying to make its way up the spinal cord. You've all probably heard of the placebo effect, something like that. This is a real big problem in pain research because we have endogenous nociceptive or anti-nociceptive pathways that are going to blunt pain signaling. Regardless of what you do, your nervous system is eventually going to turn down chronic pain. And we'll see how that works in the last part of the lecture. So we'll start our journey up the spinal cord. At this point, we know how we communicate with muscles and skin, at least a little bit. The activation of those A beta, A delta, and C fibers is going to lead to activation along the posterior column, medial lemniscus pathway for tactile sensation. And then, in this case, the spinothalamic tract is what we're talking about because this is conscious perception. But there are other components of the anterolateral pathway. We'll get to those in the next point. I realize that we do have a face, we feel in our face, but this doesn't really involve the spinal cord, so we're going to brush it under the rug for now and forget about our face until the next unit. We'll bring it back up. Pretty simple though. Trigeminal nerve goes to the thalamus. It's called the trigeminal thalamic tract. You don't need unit 3 anymore. We'll touch that again though. What we're focusing on here is what happens in the spinal cord. So, here below. For tactile sensation, this is going to be your posterior columns in the spinal cord. Posterior meaning they're in the back, and columns because they're columns that run up the back of the spine. So the name makes sense. Don't overthink it. We separate this into two different components based on whether we're in the lower part of the body or near the ground. That'll be our gracile fasciculus. That's going to be the tract, and then that's going to hit the gracile nucleus in the medulla. So the primary afferent here is going to go from somewhere out there in the body to the medulla. That's its job. It doesn't cross. So the tactile sensation remains uncrossed within the spinal cord. We're going to cross once we hit the medulla and form the medial lemniscus pathway. That's our secondary afferent. So the secondary neuron here is the one that's going to cross. This is also going to be true in the spinothalamic tract as well. So the second one crosses, whether it's painful or not. The difference is where the secondary afferent lies. So for non-painful sensation, it's up in the medulla. For lower extremities, we're going to be gracile. For upper body, cuneate. And this will come up again whenever we're talking about our cerebellar tracks. So you'll hear cuneate again later on. And there's an organization within our posterior columns. Those that arise earlier, well, lower down in the spinal cord, are going to be more medial. So your gracile fasciculus is going to be medial, and the cuneate fasciculus is going to be more lateral. So there's an organization from neck to toe, going lateral to medial. So they're going to encounter different nuclei in the medulla. The name's still going to be consistent, either gracile or cuneate. Those are going to project across the midline, locally in the medulla, and then on up to hit the thalamus. So here's where we cross. Now we're contralateral, from the medulla up. The tertiary neuron in the thalamus is then going to project to the primary somatosensory cortex. And this creates our conscious perception of touch. So if something is happening down here in our leg, those afferents get stimulated, they project on up the gracile fasciculus to the gracile nucleus, cross over, head up to the ventral posterior lateral nucleus of the thalamus, and then they project on up into portions of the cortex that deal with the leg. So there's still a map here too, from head to toe. We maintain these body maps throughout so that location actually means something. So we maintain an organization that fits with our body all throughout, whether we're in the posterior columns here, whether we're in the medulla, whether we're in the thalamus, or most importantly, when we're in the cortex. So we have some idea of where tactile sensation is taking place. 3 neurons. We can all handle that. The anterolateral pathway is going to have a few different offshoots along the way. We're just going to talk about spinal thalamic in this first part. And again, 3 neurons. That's all we're dealing with. The primary afferent is still out there in the skin, but in this case, it's going to be your A, delta, and C fibers. So those pain-sensing neurons that are going to pick up changes in temperature and pH. Those neurons are going to synapse locally in the spinal cord. You can see that down here. So they're going to synapse in the dorsal horn onto the secondary afferents. These are going to cross within the spinal cord. Within a couple of spinal segments, as they ascend, they're going to cross the midline. So within the spinal cord, we're crossed for pain and temperature sensation. Unlike tactile sensation, which remains uncrossed throughout the spinal cord. No crossing until you hit the medulla. Not true for temperature and pain. That's going to cross in the spinal cord. Yeah?
This is still the primary?
Secondary at this point. Secondary crosses. If we're crossing, it's a secondary afferent. But it is in the spinal cord. If this were the posterior column medial lemniscus pathway, absolutely it'd be a primary, but it's not, so it isn't. The primary afferent only goes from skin, muscle, joint to dorsal horn. Then crosses over. And it's going to run in the anterior and lateral portion of the spinal cord, hence the name anterolateral pathway. We're not seeing the offshoots, but we will soon enough. As it ascends from spinal cord on up to thalamus, we're going to have some offshoots along the way to innervate different brainstem nuclei. And we'll see what those do later on. We're going to hit the thalamus to encounter our tertiary neuron. We're going to hit the same area as before, ventral, posterior, lateral nucleus of the thalamus, and that'll again project on up to the primary somatosensory cortex, so we know where we hurt. That emotional response and the arousal that happens when we're hurt deals with the other thalamic nuclei that are targeted by our secondary afferents. So there's a few different tertiary neurons here. All are in the thalamus though, but in different parts of it, and thus they connect to different parts of the cortex. We'll hear these again whenever we talk about the thalamus, but we'll hear them now too. Mediodorsal nucleus. When you hear this, you should think limbic system, emotion, memory. So those secondary nociceptive afferents are going to create some sort of emotional response, and we're probably going to remember that so we don't do it again, because we're going to target the mediodorsal nucleus, and this is going to recruit emotional and memory circuits in the limbic system. So, pain sucks, right here. Where is the pain? How do I feel about it? The arousal comes from the intralaminar nuclei of the thalamus. These are kind of diffuse, they're spread out throughout the thalamus, and their connections to the cortex are similar. They're diffuse, spread out, and they're excitatory. So they just grossly arouse the cortex to help to increase our level of awareness so that we can do something. We can respond to this painful stimuli. So this kind of wakes you up. They're going to all act together to create that conscious perception of pain. Where does it hurt? I don't like that it hurts, and I remember it, and I'm aware that it hurts, and I should do something about it. And that's it. Just 3 neurons again. Well, we kind of cheated. There's a few different third neurons here. Any questions? Alrighty. Well, let's see if we can handle these and then we'll move on. Let's walk through our posterior column, medial meniscus, and spinal thalamic tracts. Let's see if we can organize these in a way that makes sense. Yeah. You were a cheerleader. I had no idea.
Were you just over?
All right. Well, let's put a little pep in this answer. We're going to start with our posterior column medial meniscus pathway. We got primary, secondary, tertiary neurons. I wanted to know where their input comes from, where their cell body is located, and then where they're projecting to, and then let's just say whether or not they cross.
Okay, so primary afferents are A beta fibers. Those are along the posterior column.
Okay, all right. So where's their cell body? Let's start
Cell
there.
bodies are in the dorsal root ganglion.
Fantastic. All right, so this is actually then, you're telling me the posterior column portion of that. Okay. Input. Where's input coming from?
I don't really know.
Well, shit. Who can help us out with that? Yeah. What's that?
The body.
The body.
Okay.
Don't overthink it. Okay. All those specialized receptors we talked about last, is that last lecture? I think it might have been. So we'll just say body, that's fine. Somewhere out there in the periphery. Where are we projecting to?
So from the lower limbs, we project to medial still.
Okay, great.
And then the upper limbs to the cuneate.
So we're going to go to the medulla, and it will either be gracile or cuneate nuclei. We're going up to the medulla. Did we cross the midline? Okay, cool. Courtney, let's handle the secondary afferent. Thank you, Leah.
Secondary, they project along the medial meniscus.
Okay, great.
I know they do cross.
All right. So you can just send this on up here. So their cell bodies are going to be in the medulla, gracile or cuneate. Where are they projecting to?
It's not the medial meniscus.
That's the pathway. Absolutely.
Pathway.
That's the pathway. Where does that pathway terminate? Well, where's this going to be located?
In the thalamus.
Fantastic. Thalamus. This goes right up here. Hell, this is pretty easy, right? So our input is going to be from our secondary afferent, C here. And where are we projecting to the tertiary neuron? Where's this target going to be? Okay, great. Yeah. And this is where the magic happens. Where are we feeling stuff? It just depends on the pattern of activity in your primary somatosensory cortex. You can directly stimulate the somatosensory cortex and create a perception of touch. You don't have to actually touch them. You can use some high-powered magnets to stimulate the cortex, and they'll feel it. Have we crossed the midline again? Okay, great. So we're crossing once. That might not always be true, but it is for here.
Great.
I know, double cross. All right. How about the spinal thalamic tract then? L.
Yes.
Let's start with the primary. What's our input? Where are we getting input from?
This spot. I don't know. The body.
Don't overthink it. There you go. Out there in the body. So this is going to be those free nerve endings. Acid sensing ion channels, stuff like that. See last lecture. Where's the cell body?
In this spot.
Yeah, pretty much. Yeah. All right. And where are we synapsing to? We're projecting where in this case?
The thalamus.
That would be a wonderful answer if that were true. It would really simplify things.
Yep.
It would simplify a lot of things. We wouldn't have to think about this guy right here, but that's not the case. Where are we hitting?
The nucleus proprius.
Fantastic.
Yep.
Out there in the dorsal horn, there's a couple different synapses you could tell me about. Nucleus proprius is fantastic. So it's still in the spinal cord. We're synapsing in the spinal cord. Notice we didn't do that here. Did we cross the midline?
Yes. No.
Which one is it?
Yes. No,
Nice.
not that. I'm sorry.
Not on this one. Chandler,
Yeah.
you're going to take it and run with it now, because these all kind of fall into place at this point.
All right.
Where's our input for that secondary afferent? Notice we've hit it, now we're in the dorsal horn of the spinal cord still. Input is coming from where?
The dorsal root ganglion.
Okay, fantastic. You got it. That primary afferent. Wonderful. Cell body located right here, dorsal horn. All right, now the new information. Where are we projecting to?
You're going to go up there to the brain.
Okay, great. Roughly what ballpark area of the brain?
Give me a second.
I'm hearing
BPL.
several of these, yes. Somewhere in the thalamus. We got a few options, VPL, intralaminar nucleus, mediodorsal nucleus. Are we crossing the midline? Absolutely. The secondary afferent is the one that crosses the midline. Notice it's the same on both. Isn't that nice? Notice we're projecting to the thalamus for both of those as well. Different parts, and thus we have different reactions to non-painful and painful stimuli. All right, great. That tertiary afferent. Just fill these in. The input's going to be coming from that secondary afferent in the dorsal horn. The cell body is in the thalamus and depends on where it is. These are all going to target different areas. So where are we projecting to if we're at that ventral posterior lateral thalamus? Where does that project to? Okay, mediodorsal, limbic system. Great, so emotion, memory. Ventral, posterior, lateral. Where are we projecting to? Primary somatosensory cortex. What does that create for us?
Where is it?
Where it is, exactly. Location. Primary somatosensory cortex. How about the intralaminar nuclei? All over the place. Diffuse. Cortical projections to create arousal so you don't sleep through the pain. Do we cross the midline again? Fantastic. So there are some similarities here, or they're both getting input from the body. That should make a whole lot of sense. That's how we're sensing what's going on in the body. Both primary afferents are in the dorsal root ganglion. Tertiary afferents, all in the thalamus, different parts of it. The secondary is a bit different in terms of where it's located. The spinal thalamic tract is going to be there in the spinal cord. Posterior column, medial meniscus is going to be in the medulla. But hell, they both cross the midline. They both project to the thalamus. So they got that in common. There's not too many differences here when you organize it and kind of think about it a bit. All right, how about that second question? What are we dealing with? A couple different spinal cord lesions. Okay. Claire. This is how I think of people. So we have a left hemisection. We'll put it like that. Let's follow these up. Let's follow our posterior column medial meniscus pathway. Are we going to cross the midline?
No.
No. We're going to project up uncrossed into the medulla. How about our spinothalamic tract?
Yes.
Excellent. We're going to be crossing the midline. We're going to synapse locally. And that's going to head on up the thalamus. So when we have this hemisection here, half the spinal cord is damaged. How's that going to affect sensation below that? Let's say in the left leg, we feel anything, if we lost anything.
We would lose our non-painful stimuli.
Fantastic.
So perception things.
Yeah. This is severed, no more input. Yes. But you're telling me our,
We wouldn't have an effect on the painful stimuli.
okay, so we can feel temperature, we can feel pain. How about in the right leg?
It's the opposite.
Fantastic. This is why I paid, where things cross. So here we'll still feel tactile sensation just fine, but it will feel a bit odd because we won't feel temperature and pain. How about the posterior injury there? Adam. Posterior half of the spinal cord. What's running along the posterior half of the spinal cord? True. What type?
Non-painful.
Exactly. Yeah, posterior columns. So, how are we going to affect this leg? When we have that injury up here at T10, let's say. Posterior spinal cord is damaged. Let's just assume it's complete. That'll make the answer a little cleaner. What happens to sensation in this leg? Okay, great. Tactile, painful, thermal.
Non-painful.
Okay, great. The tactile sensation. How about this leg? Same thing, exactly. So here we're separating out the different types of sensation because they're located in different parts of the spinal cord. They cross differently and they run differently as well. The anterolateral pathway runs in the anterior and lateral portions. The posterior columns run in the posterior portion. Any questions on that?
If it was just like the question, it was just the left, then it would just be that side that was affected.
Just the left portion of the posterior column? Yeah, exactly. You have then ipsilateral loss of tactile sensation because they haven't crossed there. Okay. So we're going to talk about unconscious perception. And then we're going to come back to pain because that was a little trickier for folks. So I want to end on that. Plus, we got to talk about the rest of the anterolateral tracks. So there are these offshoots that don't make it to the cortex. Therefore, you are not consciously aware of them. But they're doing stuff. And we're going to come back to them in the third point of this talk. More specifically, this spinal mesencephalic tract right here, where we stimulate the periaqueductal gray. That's kind of important. There are other offshoots along the way. The spinal olivary tract, that's going to stimulate our olive. The olive provides very strong input to the cerebellum to help modify the circuitry within it so that we can learn, at least non-conscious motor learning is what's going to happen when our olivary nucleus is stimulated. And we'll talk about that again whenever we hit the cerebellum. But part of the input to help drive that olive input comes from pain. If you fall down and hurt yourself, this should tell you that you need to refine your circuitry for how to stand and walk. So this is probably very important early on. My girls fall down all the time because they're just now getting their sea legs. They fall a lot. And so they're going to have that spinal olivary tract providing input to the olive to say we should fix our cerebellum. This is not working. We keep falling down. There's going to be input to the reticular formation as well. We'll hear about them whenever we talk about the brainstem in the next unit. But this is just a collection of brainstem nuclei that provide diffuse excitatory input to the cortex. They help keep us awake. This is kind of like the intralaminar nuclei in the thalamus. This is another source of cortical stimulation in response to pain. Again, you don't want to sleep through the pain. You want to be well aware of what's going on so that you can respond to it. That pain might be something nibbling on you, trying to make a meal of you, and you'd like to get away from it. So we have a secondary route to stimulate the cortex down here in the brainstem. And then there's this offshoot in the midbrain that's going to stimulate the periaqueductal gray and help provide negative feedback to this whole system. You always want to see this. You want to see negative feedback loops. If the signal isn't turning itself off, it runs the risk of becoming noise. And so here is going to be our negative feedback loop. It's pretty straightforward. Just a few neurotransmitters and receptors to get under your cap. It'll make a whole lot of sense. Other tracts that don't make it to the cortex but are certainly important would be those that run up to the cerebellum. So the spinal olivary tract is going to kind of indirectly hit the cerebellum via the olive sometimes. The Spinocerebellar Tracks are going to more directly target the cerebellum so that it's aware of what are we feeling, so what's our body position. Your body position is going to affect what sort of movements you're going to execute. If you want to, let's say, I don't know, pick this up. Well, if my hand is closed, I know I need to open it. It's already open, I don't need to do that, right? You need to be aware of your body position if you're going to properly regulate your movements. If you're starting to lean over, you want to make adjustments to your balance so that you don't fall over. All of these adjustments that are carried out by your cerebellum without you having to do any thought require some sort of feedback. And there's a couple routes for feedback. It depends on the location in the body, whether it's going to be our posterior spinocerebellar tract or the cuneo-cerebellar tract. In this case, rather than just running up along the posterior columns, the A-beta afferents are going to make some local synapses along the way. For the posterior cerebellar tract, we're going to synapse locally in the spinal cord. This is also going to run up as well, keep that in mind. But we're going to synapse locally in the spinal cord and create the posterior spinocerebellar tract. So a different nucleus in this case, not the nucleus proprius, but in this case, the dorsal nucleus. It's going to handle different information. This is not pain. This is just feedback to create that non-conscious somatosensory input for the cerebellum. So we synapse locally, and then these neurons are going to project up via the inferior cerebellar peduncles, once they hit the medulla, into the cerebellum. So we're providing some input about the lower body. What's the position of our lower limbs? The upper limbs are going to be handled along the cuneo-cerebellar tract. So in this case, our A-beta afferents are going to project on up the posterior columns, and rather than synapsing the cuneate nucleus, there's this little offshoot called the accessory cuneate that doesn't create the medial lemniscus pathway. Instead, it projects to the cerebellum, again along the inferior cerebellar peduncle. Notice that these are ipsilateral. Input to the cerebellum is ipsilateral. No exceptions. Same side of the body here. It's contralateral in the cortex. Cerebellum remains ipsilateral. The input for both of these is going to be the inferior cerebellar peduncle. And this is just going to provide the cerebellum with essentially an instantaneous map of body position so that it can properly refine movement to make sure we don't fall over and that we execute movement smoothly. The actual movements that are taking place also get relayed back to the cerebellum via two different tracts. There's again lower and upper body. They're going to project along different tracts. So not the posterior spinocerebellar tract, but in this case the anterior spinocerebellar tract. So just in front of that. Again, we're going to synapse locally. Rather than getting immediate input from the body, instead, our sensory neuron here is going to be located in between the dorsal and ventral horns in the spinal cord. So it's somewhere in between the sensory and motor portions of the spinal cord. It's going to receive input essentially about the reflexive behaviors that are going on, any motor output. So these neurons are going to be privy to motor and sensory information that's going on within the spinal cord. In other words, what are we actually doing? Not plans, nothing like that. What's the actual activity in the spinal cord? Let's relay that back to the cerebellum. Since they're in between dorsal and ventral, we call it the intermediate zone. It's in between them. These are going to cross. They're going to cross locally and head up, not in the posterior, but in the anterior spinocerebellar tracks. It's going to project all the way up until we hit our pons here. Then we're going to head down in the superior cerebellar peduncle. So there's a bit of a difference. We've crossed and we're using a different peduncle, but then we cross again. So it remains ipsilateral. It's a double cross. You gotta watch out for these. But it's still ipsilateral. Left side of spinal cord, left side of cerebellum. So all tracts are ipsilateral. This is still true. I realize that the crossing cross back, but that makes it just ipsilateral. The upper limb portion of this is very minor, not well characterized. It's only from a couple different spinal sections, C7, C8, very minor tract. It probably also projects up to the superior cerebellar peduncle and double crosses. It might also just project directly via the inferior cerebellar peduncles. It's so small, we don't know a whole lot about it. This one's called the rostral spinocerebellar tract. But again, there's a pair of tracts. These are for sensory input, what's my body position? These are for the motor output, what's my body doing? The cerebellum needs to know both of those so they can properly regulate our movements. If you're already leaning over a bit and you're executing a movement that's going to further move your center of gravity away, well, you need to adjust so you don't fall over. And your cerebellum is going to handle that without you thinking about it. Because notice, we didn't touch the cortex at all in any of these pathways. This is all unconscious. So whenever you get good at a movement, whatever that may be, whether it's throwing a ball or playing a scale, you do it with little thought. But it just happens. You just think, I want to play the F major scale. And then you run on up with little thought. Your cerebellum's handling that. Once you learn how to execute a movement, it happens without the cortex anymore. It doesn't really guide the actual fine movements. That's all going to be down here. And largely that's through trial and error. You do something, it doesn't work, Olive says it doesn't work, and your cerebellum tries again. Any questions on this? All right. Let's go through these, and then we'll talk about pain, the ending of pain, that is. Okay, so there's a few offshoots in the anterolateral pathways. Let's go through those. All right, here's our anterolateral pathway. We've got a primary afferent, synapses locally, crosses over, heads on up. We've already gone over this, so the spinothalamic tract is going to terminate here in the thalamus. There's a couple different stops that can happen along the way, so we'll send out little offshoots. Let's talk about some of those, Alex. I realize it's not red meat or coffee shops or beer, but it's good enough. Hey, this is red ink though.
It is, that's close enough.
Yeah. Okay, so what are some offshoots in the anterolateral pathway? Where else are we synapsing? And what do those things do for us?
The spinal olivary.
Okay, great. Spino-olivary. What does that last part of you? What does that last part tell you? Where are we hitting?
Olive.
Fantastic. We're going to hit the olive. We're going to hit the superior olive. Now what? Why does that matter? It looks like an olive, believe it or not. So this is a nucleus that we call the olive in the medulla. So here's, that's a great question. What the hell is an olive? So here's our pyramids. So this is the front of the medulla. Coming off of those, we have our olive. Above that, we'll have our pons at some point. But the olive is this secondary bulge here. There's our olive. Tastes great in a martini. You cut it in half, it kind of looks like an olive. What does the olive do for us? Alex Rod.
Motor learning.
Thank you. Yeah, motor learning. Because the olive is going to project to which part of the brain here?
Cerebellum.
Fantastic. When you hear motor learning, you should think cerebellum. And you should also think olive. Then you should think, man, I could use a drink. Motor learning. If something hurts us, we should probably remember that. And we should probably refine our movements so that we don't fall down again, for example. There should be some learning component. This is that non-conscious learning that's going to take place. Thanks, Alex. Kate,
What's that?
what's another offshoot?
You have the reticular formation.
Great, the spinal reticular tract. What does that do?
Arousal.
Fantastic. So this is going to project widely. I hope that suggests that to you. The cortex. So here we're going to have arousal. And I guess down here I should write learning. So that'll help your learning. Do we have any other offshoots? Arlen.
Yes. We have the spinocerebellar, which goes to the superior colliculus.
Oh yeah. Shoot, I didn't talk about that one. So what does that do for us?
That is, so the superior colliculus, they handle your eye movements.
Fantastic.
So like when you're looking at something, if you turn your head, you stay looking at that thing.
Excellent. Yeah, you should probably take a look at whatever is causing pain. We'll pretend like that was always there. Britta.
The perioccipital today.
Okay, great.
Spinomesencephalic.
Yes, we're going to hit the midbrain. Okay, again, we're still in the midbrain. In this case, periaqueductal gray. What does this do for us?
It's a negative feedback with pain modulation.
Excellent. This is the focus of the next several slides. No cortex in any of these except that spinothalamic tract. That's why that one enters our conscious awareness. These others don't. All right, how about the, in this case, posterior spinocerebellar and cuneo cerebellar tracts? They have something in common, but they're a little different. Lauren.
So, the PCML crosses.
Hold on now. You're getting ahead of us. Second question. Here, I just want to have us talk a bit about the posterior spinal cerebellar and the cuneo-cerebellar tracts. So what do they have in common?
They provide information about position.
Fantastic. So cuneo-cerebellar, deal with the arm, and then the posterior
The lower extremity.
leg. Fantastic.
And they're both ipsilateral.
And they're both
Ipsilateral.
fantastic. All of our spinocerebellar tracts are going to be ipsilateral. Right. And so these are both about position. In this case, the arms. In this case, the legs mostly. So upper, lower. Can you just tell me a bit, like, why do we call this the cuneo-cerebellar tract? What is that cuneo suggesting to us? Have we heard something like that before in this lecture? Yeah, what was it? Fantastic, yeah. So we're gonna project up. Is it to the cuneate nucleus? Fantastic, yeah, so it's kind of like the cuneate, it's right next to it. It'll be the accessory cuneate nucleus. From there, we'll hit the cerebellum via those inferior peduncles. How about our posterior spinocerebellar tracts? Where are we synapsing here? We going up to the cuneate?
Dorsal nucleus.
Yeah. So we're going to synapse within the spinal cord. I had enough of the medulla here. Throw it. Dorsal nucleus, somewhere around there. We're not projecting up in those posterior columns in this case. We're going to head around the side here. Are we still going to use the inferior cerebellar peduncles? Absolutely. So there's another commonality. A little different. Different parts of the body. Slightly different tracts. Notice they're both still posterior. One is running in our posterior column, the other is a little off to the side. One synapse is in the medulla. And that should make sense because your upper limbs are going to enter the spinal cord close to the medulla. Lower limbs, that's a little far removed. So we need a local synapse there, and then we create this new tract. And they both deal with position. All right, Ashley, let's hit that last one there. PCML, spinocerebellar tracts, corresponding side of the body, and then whether they're conscious or not.
The PCML gives us conscious feedback while the spinocerebellar tracks give us unconscious, so we're able to refine our different motor movements.
Okay.
And then the PCML gives us info about the contralateral side of the body while the spinocerebellar stays on the same side.
Fantastic. Yeah. Okay. Any questions here?
No.
No. Good. So if we make it to the cortex, we're aware of it. If we don't, we're not. Those things that don't make it to the cortex do a variety of things. Depends on where they hit. If they hit the cerebellum, they're going to help refine movement. If they hit the reticular formation, they're going to stimulate arousal. If they hit our superior colliculus, they're going to move our eyes. If they hit the periaqueductal gray, well, then they're going to help modify nociceptive signaling. Because pain, like any other signal, needs to be terminated at some point or it becomes noise. There's a host of positive feedback loops that exist in nociceptive signaling. There's your axon reflex, peripheral sensitization, central sensitization. Pain has many ways of amplifying its signaling. So there needs to be some break in place, some check that's going to turn off pain. And you probably noticed that pain is usually most intense right when it happens, and then over time your cut will feel a little better. Part of that's healing, and part of that's just natural painkillers. And because we have natural painkillers, we have to be very aware of placebo effects whenever we're doing any study with pain. Pain is self-limiting. It's going to turn itself off whether you do anything or not. So you always have to have some control group to get some idea of how much of this is contributing to your data. There's a few places where we're going to gate pain. One of them is pretty quick, and is going to be effective for very low levels of pain. And that's just right there locally in the spinal cord. That's what this is, believe it or not. So here's our spinal calamity tract, primary afferent, secondary afferent. We're in the dorsal horn. There's a whole bunch of other stuff. The spinal cord contains its own logic. This is still a part of the central nervous system. And I think we all said at the beginning of class that the central nervous system is there for information processing. If you're going to process information, you're going to need more than just a direct synapse right here. You got to have some circuits. And there's a lot of circuitry involved here. We're going to simplify things. Don't sweat it. But there's a lot. There are a variety of inhibitory neurons and excitatory neurons in place here. That's what creates our logic. That's what allows processing, having additional neurons there to refine whether or not this is going to be a strong synapse or a weak synapse. Well, if we stimulate a bunch of inhibitory neurons, like this one with GAD65, that's the enzyme you need to make GABA, and it's blue, so both of those things are telling us it's inhibitory. We can decrease activation of our nociceptive afferents. Alternatively, if you increase the activity of these excitatory interneurons, and they're all over the spinal cord, those can increase excitatory drive to our nociceptive afferents and allow for pain signaling to proceed through their spinal cord. While there is a lot going on here, let's just think about our primary and secondary afferent. So here's pain. If this gets activated, it's going to stimulate the thalamus and create some conscious perception of pain. If this isn't activated, it won't. We won't perceive pain. It gets excitatory input from its primary afferent, and then there are inhibitory interneurons that are going to provide GABAergic or glycinergic input to decrease its excitability. So they're going to open up chloride channels and resist movement away from rest. Those get stimulated by these. Have we heard of A beta afferents before? Great, non-painful, just tactile sensation. So if you bump your knee and you rub it, it feels just a little bit better. Here's why. Those tactile A beta fibers are going to be stimulated by the rub. There are inhibitory neurons within the dorsal horn that will provide inhibitory input to nociceptive afferents. So after you bump, you rub to provide a little bit of GABA and glycine here at this synapse, so that you have decreased input along your spinal thalamic tract. Less pain. This only works for minor injuries. Anything more severe, we're going to have to resort to opioids. But for something simple, this works. And you have to have this in place. I think we've all accepted that everything is mechanically gated to some degree, even your eyeballs. Undoubtedly, those A delta and C fibers are going to be mechanically gated. Part of their job is to sense what's going on in the body. Every time a part of your body receives pressure, these are going to get some degree of activation. We need to cancel that out so that everything doesn't hurt. If we didn't cancel that out, there'd be minor activation of the spinal thalamic tract and a little bit of pain every time you're touched. That's not the case because of all this, the spinal circuitry that says if we have sufficient activation of non-painful fibers, we're probably just getting touched. It's probably just pressure. So it's the ratio of these things. And what helps bias it toward only non-painful sensation would be these inhibitory interneurons. So that when someone's tapping our shoulder, both of these fibers are activated. But this activation gets shunted via these inhibitory interneurons. And this is going to arrive first. A beta, much bigger, faster conduction velocity. This is going to arrive at the spinal cord first, stimulate some inhibitory interneurons so they can dump GABA and glycine here and make sure we don't feel pain when we're not supposed to. And you can rub your knee and it'll feel a little bit better. Now, if your leg is cut off at the knee, you're going to need a little more than that. Rubbing it won't help. We're going to have to recruit exogenous opioids nowadays, but before you just have to wait a while and let your spinocerebellar tract do its magic. We're going to start backwards here. I think that's going to help us understand this, but only going through this many, many, many times will help you understand it. I'm sorry. But it's really not that tough when you think about it. Many, many, many times. There's two neurotransmitters that are going to help regulate pain. And they're going to arise from the brainstem. There's descending tracts that are going to allow them to spit out either norepinephrine or serotonin in the dorsal horn. And those are going to decrease nociceptive signaling in a couple different ways. The norepinephrine is pretty straightforward. Noradrenergic neurons in your locus coeruleus are going to release norepinephrine. That's going to stimulate norepinephrine receptors. We need to know which kind, of course. In this case, it's alpha-2, and that's GI coupled. Excitatory or inhibitory? Fantastic. We're going to be activating long-lived inhibitory neurotransmitter receptors on our nociceptive fibers whenever we release norepinephrine from the locus coeruleus. The other neurotransmitter that's going to be dumped out there in the dorsal horn would be serotonin. This arises from a different nucleus, the raphe nucleus. The magnus raphe is just a large collection of serotonergic neurons. The raphe nuclei are going to run throughout your brainstem. We'll hear about them again. And when you hear raphe, you want to think serotonin. The magnus raphe nucleus is going to project downward into the spinal cord and release serotonin. It's also going to target the locus coeruleus so that we get additional noradrenergic input as well. So serotonin is going to do two things. It's going to act in the spinal cord. It's going to stimulate inhibitory neurons down there. Again, we need to know the receptor. Serotonin. It's going to act postsynaptically on 5-HT, that's just serotonin, 2A and 2C, both of which are GQ. Is that excitatory or inhibitory? Fantastic. We're going to increase calcium levels in our inhibitory neurons, so they're going to dump additional inhibitory neurotransmitter onto nociceptive afferents. So we're going to inhibit pain signaling via this interneuron here. They'll also act presynaptically via cation channels. This is the only neuromodulatory channel that's actually ionotropic, 5-HT3. Everything else is metabotropic that we're dealing with. When the serotonergic neurons in the raphe nuclei are stimulated robustly, they're going to release neuropeptides. Again, you have to burst fire if you're going to release neuropeptides. They're expensive, and they're held away from the active zone. When we have sufficient excitatory input to the raphe nucleus, they burst fire and they release substance P. This is what's going to activate neurons in the locus coeruleus. Substance P is going to bind to GQ-coupled neurotransmitter receptors. Are those excitatory or inhibitory? Fantastic. So we're going to excite noradrenergic neurons, so we're going to bump up this signaling. And what that's going to lead to is a reduction in nociceptive transduction. Let's have a look at why we think that. The x-axis is just showing us different time points. B1 would be baseline, 5 minutes or 15 minutes after they give a substance P injection. And then Y here, the y-axis is just the amount of pressure we had to apply to the paw to make them withdraw it. Paw withdrawal is going to take place whenever their paw hurts. The amount of pressure that you have to apply relates to the amount of nociceptive signaling that's taking place. What's that? This is a rat.
Okay, you say pot, you say dogs. I was thinking
Okay, not dogs here, no, rats. So, this is a common readout for pain signaling. When you burn the paw, this value drops. You need less pressure to cause pain. When you blunt nociceptive signaling, you need more pressure to cause pain and make them withdraw their paw from the filament. After we inject substance P, that's what SP is, along with some saline that doesn't do anything, you'll notice that the amount of pressure needed for them to withdraw the paw increases. So there's decreased painful signaling. You need more pressure to sufficiently activate those A delta and C fibers. Not the case if you antagonize our alpha-2 adrenergic receptors. And that's what this filled bar is showing you. When you decrease noradrenergic signaling, in other words, when you block this, no decrease in painful signaling. So we need noradrenergic input in the spinal cord. That's what this is telling us. Substance P is somehow increasing the activity of noradrenergic neurons. And that is absolutely fundamental for this, for that anti-nociceptive activity of substance P. Substance P needs its neurokinin 1 receptors, because if we antagonize those, we see the same thing. Substance P still decreases nociceptive signaling, but only if you let it act on its receptor. Taken together, what this is telling us is that when substance P stimulates its neurokinin 1 receptor, we decrease nociceptive signaling. And that's because those neurokinin 1 receptors are located on our neurons in the locus ceruleus. They'll release norepinephrine that actually causes this, because without the activity of your alpha-2 adrenergic receptors, you don't see this decrease in pain signaling. So a couple different neurotransmitters there. Norepinephrine, serotonin are going to act down there in the spinal cord. Those serotonergic neurons also synapse in the locus ceruleus and release substance P to further recruit these noradrenergic neurons. This is all going to be gated by opioids. We're going to continue our journey backwards away from the spinal cord. What's controlling that circuitry? The locus ceruleus, the magnus raphe. Well, that would be our periaqueductal gray. Neurons here provide excitatory input to the raphe. So if our periaqueductal gray projection neurons are active, they're going to provide excitatory input down here to the raphe nucleus. That's going to cause them to burst fire. They'll stimulate the locus ceruleus. They'll also release serotonin locally in the spinal cord. So what determines whether or not we have stimulation of this pain gating has to do with whether or not neurons in our periaqueductal gray are active. Have we heard of anything that provides excitatory input to the periaqueductal gray? Yeah, the anterolateral pathway. Yeah, there's an offshoot there. So when we have active pain signaling, we're going to provide excitatory input up here, right where we need it, to stimulate all that stuff that we just brought up. It's negative feedback. This is also going to be gated by higher brain structures. The hypothalamus is going to provide disinhibition to those projection neurons. So it's going to release an opioid called enkephalin that binds to mu opioid receptors. Those are GI coupled, excitatory or inhibitory. Fantastic. So we're going to inhibit inhibitory neurons in the periaqueductal gray. That's what this little cartoon is showing you here. Oops, we'll get to that in just a second. So when our hypothalamus provides enkephalin input into the periaqueductal gray, those neurons that are normally inhibiting our output neurons get inhibited. This is a common mechanism of activation. It's called disinhibition. We remove inhibition, and that allows excitation via that spinal mesencephalic tract. When the periaqueductal gray is active, the raphe is active. When the raphe is active, the locus ceruleus is active. The raphe and locus ceruleus provide serotonin and norepinephrine to blunt nociceptive signaling. Enkephalins are also going to come up down there in the spinal cord too. There's local release of opioids as well. So here's everything that's going on. Simplified. If we stimulate our periaqueductal gray, which we will if we're having any sort of pain, and we'll allow robust stimulation there if we have input from the hypothalamus to disinhibit the projection neurons. Output from the periaqueductal gray is going to activate these blue serotonergic fibers from the raphe, then via those, the green noradrenergic fibers from the locus ceruleus. What they're going to do down in the spinal cord is inhibit this, our anterolateral tract. Here's our primary afferent, lives out there in the dorsal root ganglion. Here we are in the nucleus proprius. There's that secondary afferent. It's going to cross the midline eventually and project on up. If we inhibit this synapse, we inhibit pain. We won't feel pain. So you could take some exogenous opioids and they'll act locally. They'll also act up in the periaqueductal gray as well. Or your hypothalamus could release them, stimulate periaqueductal gray, which then stimulates the serotonergic input. Serotonin is going to stimulate inhibitory neurons. These are going to provide GABAergic, lysergic input at this synapse. They're going to shunt the excitation that's occurring there. When they burst fire, they're going to then release neuropeptides. The neuropeptide in this case is enkephalin. It's still going to bind to mu opioid receptors, in this case on our nociceptive afferents. Mu opioid receptors are still GI coupled, so are they still inhibitory? Absolutely. So we're going to inhibit quickly via GABA and glycine, and then over the long run with enkephalin. We're going to provide strong inhibition of this synapse. There's also that noradrenergic input as well from the locus ceruleus. That's also going to inhibit our nociceptive afferents. Not via mu opioid receptors, but through those alpha-2 adrenergic receptors. Same signaling under the hood though, GI coupled. So is that excitatory or inhibitory? Inhibitory. Fantastic. There's some different neurotransmitters, but they're all doing basically the same thing. There's ionotropic and metabotropic inhibition going on here. Both of those are going to decrease the excitability of this pathway and blunt pain. This is how opioids are going to work. Now, despite what's going on in the periphery, there is no excitation of the secondary afferent. There is no conscious perception of pain. Now you'll notice here, we got a little negative feedback. Norepinephrine from the locus ceruleus is going to help turn this whole system off by decreasing activity of those serotonergic neurons in the raphe. That's just responsible signaling right there. The main thing that you need to worry about is the effect right here. How are we decreasing activation of that secondary afferent? If we can prevent it from firing, we can prevent ourselves from hurting. And there's many ways that we do it, via inhibitory, fast synaptic signaling, or more long-lived inhibitory signaling. And that's it. Any questions? I know, pretty laughable, right? How could that be confusing? Say it a few times, it'll make sense, I promise. And if it doesn't, come see me. The pain will stop once you understand it. Go through these and then we'll call it a class. Brianna, why is it that rubbing my knee is going to help after a bump?
So when you rub your knee, you're mechanically opening the cation channels for the A betas, which are faster at arriving to the spinal cord.
Mhm.
And those, so those are like non-painful sensation, so that helps decrease the pain, like the painful sensation that comes from the A deltas and the C fibers.
Ha,
Um,
don't overthink it.
I'm not sure.
How can you translate excitatory activity into inhibitory activity? What's the easiest way of doing that?
There's more,
What's that?
there's just more of
Okay, and what stimulates inhibitory activity?
Is inhibited or activated?
Yeah.
Well, just stick an inhibitory neuron in there. Don't overthink it. It'll become tough if you do that. So I want to turn excitation into inhibition. There. Done. Now when this neuron fires action potentials, it leads to action potentials in this neuron, which is then going to stop activity in this third neuron. Who cares what it does? Leave it open. Because this is going to spit out an inhibitory neurotransmitter. So what's going on in the spinal cord? Let's say here's my primary afferent. We're synapsing locally, we'll cross and head on up here. How does an A beta afferent inhibit this? Brianne, again, don't overthink it. How can we inhibit this whenever we stimulate, let's say, slightly bigger A beta fiber that's gonna run up there? What else can it do to inhibit this?
It doesn't allow, I guess it doesn't allow for the, like the painful sensation to be activated
Okay, great. How?
by inhibiting it.
Fantastic. Does it itself release inhibitory neurotransmitters?
I'd say yes.
Okay, that would be nifty if it did, but it doesn't. So let's just stick an inhibitory neuron in there. So it excites an inhibitory neuron, and now, all of a sudden, we're dumping out inhibitory neurotransmitters. Don't overthink it. If you want to make a positive and negative, multiply by -1. That's essentially what we're doing. If you want to allow excitation of an agonist muscle to cause inhibition of an antagonist, put an inhibitory interneuron between that motor neuron and the antagonist. So when you excite the neuron to contract this muscle, you're inhibiting the neuron to contract the antagonist. Inhibitory interneurons are where it's at. These have expanded far more throughout evolution than excitatory neurons. Okay. Now let's see if we can understand why we need opioids. If we're not just bumping our knee, what if we're getting surgery or just had surgery? What goes on there? Daniel, let's start filling in this. You don't have to give me all of it. I'll give you some of it.
All right.
We got primary nociceptive fibers. Here's the secondary. We're going to head on up. Maybe you put something up here. I don't know. And then here's the local circuitry.
I'll just read what I have. Tell me if I'm wrong. All right. The interneurons that will inhibit the nociceptive afferents have those mu opioid receptors on them, which are stimulated by those either internal or external, like enkephalin or morphine, the opioids there.
You're saying inhibitory neuron down here?
Yes.
Okay. So we got an inhibitory neuron.
And these receptors, they're deep protein coupled, so the impact whenever you activate them is greater and lasts longer than your simple mechanical activation.
Okay.
So that better pain killing.
So I'm going to make red enkephalin, and let's make green will be GABA or glycine. There's a mix. So these are going to spit out GABA and glycine. What causes them to spit out enkephalin? What has to happen? It's a neuropeptide, by the way. We're going to release neuropeptides.
We have to have a lot of excitation.
There we go. We got a burst fire. So something has to be exciting this. Kayla, let's move on up here. What's exciting our inhibitory interneuron here? What's making you burst fire so that we can release enkephalin?
The serotonin from
Oh, okay. There's serotonergic input descending from the raphe nucleus. So you're telling me that's going to excite?
that. GABA.
Okay. Okay, great. How does it do that?
Because it stimulates inhibitory neurons, which will inhibit the primary and secondary, like you've shown in the picture.
Okay, great. Now there's many ways to excite things. Which receptors are we talking about for serotonin? I'll give you the first three. I took the easy one. Not one.
2
There we go. Yeah, 2A, 2C.
and 3.
Okay, great. And then 5HT3. What kind of, are these channels? Are they metabotropic? What are we talking about here?
The 2A and 2C are metabotropic, and then 3 is a cation channel, and that's the only one that's not.
All right, and it's G what?
Q.
Fantastic. And we should all be thinking excitation. When you have more calcium floating around, you can spit out more neurotransmitter. You're going to be more excited. Okay. Well, hell, what stimulates these neurons? So let's go up here. We're in our, you said raphe. It's going to project downward. And then we'll see what happens over here. Mackenzie, tell me about the raphe and what's stimulating the raphe.
So the raphe is stimulated by the periapital gray matter.
Fantastic. Of course, not always. There's these inhibitory interneurons that are going to be inhibited by enkephalin from the hypothalamus. I'm just going to kind of breeze us through some of this because I'm already taking too much of your time. You may leave at any time, by the way. For those of you who are sticking around, what stimulates the periaqueductal gray besides this enkephalin? Anything over here, maybe? Fantastic. So when we have pain, we start this whole process here. And I think we've left off one important population of neurons. What else do we have? Sydney, you didn't leave yet. Big mistake. What's the other population?
What was the question?
So what don't we have up here that we talked about? We got our inhibitory interneuron, we have serotonergic neurons. What other neurotransmitter have we brought up in this third part that's not here?
Yeah, noradrenergic.
Fantastic. What haven't I used? Let's say this. Brown. Okay. So in the locus ceruleus, we're going to provide noradrenergic input to C. All right, what is that doing for us?
Still me?
Yeah.
Oh. Inhibiting nociceptive fibers.
Great. How? What receptors are we acting on? Sorry.
The adrenergic receptors.
Yes, alpha 2. And what's their coupling?
GI.
Fantastic. Excitatory or inhibitory?
Inhibitory.
Excellent. So we dump out norepinephrine. We're inhibiting our nociceptive afferents. There's a little feedback. Who cares? And let's not forget the RAFA is going to stimulate that via substance P. Okay. That's it.